Hey guys, welcome to part 3 of substitution, using substitution to anti-differentiate definite integrals. And the last part is just a couple of slides. We deal with two functions, when f is even and when f is odd, and these are symmetric functions. So if f is even, we know that f of negative x is equal to f of x. So if that's true, then the following integration is true. So from negative a to a of that function is actually equal 2 times that integral from 0 to a of f of x dx. Now if f is odd, we know that f of negative x equals negative f of x. Then we know that the integration is 0. The area under the curve would be 0. So let's look at two examples, one of each. Now let's look at x to the 6 plus 1. This is an even function, and you can tell by our notes here, f of negative x is equal to negative x to the 6th power plus 1. Anything to an even power is positive, so you just get x to the 6 plus 1. So those two functions are equal. So this function is even. So when we integrate, we can go from, let's say, negative 2 to 2 of that x to the 6 plus 1 dx. That's going to be equal to 2 times the integration from 0 to 2 of x to the 6 plus 1 dx. So we integrate, x to the 6 becomes 1/7 x to the 7, and 1 becomes x. And we integrate from 0 to 2. We evaluate. So you plug 2 in for x, and you plug 0 in for x, and we get 1/28 plus 2, and the simplification of that becomes 2/84. Our last example is an easy example. If you can show that the function is odd, then the area under the curve from negative 1 to 1, let's say, is 0, or from negative 2 to 2 is 0. So this function is odd. F of negative x is negative x cubed, and the opposite of f of x is also negative x cubed. So we know that from, let's say, negative 1 to 1, the integration, the evaluation of that integral is just 0. There's no area. Okay? So that does it for section 5.5, and we'll see you next time.